hashtag AskNASA or commenting in the stream wherever you're watching this. And let's start with a few questions now. Our first question is from @Vanil Sahu on Twitter, who asks, is there any reason behind naming the missions Da Vinci and Veritas? Let's do Da Vinci first and then Veritas.
Well, who doesn't love Leonardo da Vinci, the great Renaissance thinker, innovator, artist, scientist, technologist? He invented helicopters. He painted the Mona Lisa. So what we want to do in taking his name, which is also the acronym for our mission, Deep Atmosphere Exploration of Venus with imaging and measurements of chemistry and noble gases, by taking his great name, cataloged in 500 years of history, and applying it forward to Venus, we want to see the new Venus rising in the view of Leonardo. And Leonardo painted the Mona Lisa, one of the most famous paintings of all time. We think there's a Mona Venus waiting, and we want to discover that together for all of humanity. Wouldn't that be beautiful?
Well, Veritas is also an acronym. It stands for Venus Emissivity, Radar Science, Interferometry, Topography, Interferometry, and Spectroscopy. But it means truth. And, you know, it's been so long since we have been to Venus that there are these ideas from about 30 years ago that I like to call myths that are still floating around about Venus. But we've learned so much about the Earth and other planets that they are really outdated ideas, and we are excited to bring new instruments to Venus and reveal the truth about Venus.
That's a very good answer. I like it. @KDasgupta18 on Twitter asks, which side of Venus will the exploration be carried out? The warmer sunlit side or the colder sun-hidden side? I'll start with Dr. Smrekar for this one, and if Dr. Garvin, you want to add on, feel free.
So as an orbiter, we see both the sunlit and the dark side of Venus. So we're constantly going around the planet and going from one side to the other, in fact. One of our instruments likes to primarily image on the cooler night side, our spectrometer that will allow us to get at the composition of the surface. So that instrument only operates on the night side because the glare off of the clouds is too intense to allow us to see the surface on the day side, but our radar instrument can see the surface all the time. So for the most part, we are operating on both sides.
Well, and Karen, if I may add, for Da Vinci Plus, we're going in with our probe, our flying rover, on the day side over a mountainous region known as Alpha Regio, the first radar bright area seen from Earth with radio telescopes like Arecibo. And so we're going to land in this mountainous zone. It's twice the size of Texas. That's pretty big. We're going to come in there and see the atmosphere on the sunlit side, so we have lots of illumination. You might think it's dark on the day side of Venus, but it's not. And as our probe comes through the clouds, roughly at maybe 90,000 feet, we'll start to see that surface. And it will get sharper and sharper. We'll measure its composition. We'll see it in 3D using new machine vision methods. And eventually we'll see human scale features as if we're coming in on a helicopter or in your backyard drone. So we're going to use the day side. But as we get there, we're going to visit Venus twice on flybys, taking movies of the upper cloud dynamics using ultraviolet cameras so we can track cloud motions to look at the climatology. So while we go in on the day side, we will also see some of the big Venus that Sue's mission will see.
Great, thank you. Our next question is also a Da Vinci question. It is from Sohaib24188610, who is from Twitter, and asks, can the Da Vinci Plus probe capture images of the surrounding landscape after it lands on the surface?
So the Da Vinci Plus mission does not require landing. We call ourselves a landerless lander, because we make measurements all the way through the atmosphere as if we're landing ourselves, and then we don't have to land, because we'll get all of our data. As you can see, the probe being released from our mother spacecraft developed by Lockheed Martin. We'll get all those data back through our mothership back to Earth. But if we survive landing, we have the capacity to operate for a few tens of minutes. But we think our final images and final chemical measurements made maybe 100 meters above the surface, and here we're in the clouds, flying through that area about 100,000 feet high, will show us features as small as baseballs, hockey pucks on the surface. So we could see that Venus almost as if we've landed. And the probe has instruments that can measure the chemistry, temperature, pressure, composition, all the way down, literally as a kind of a drive-by chemistry lab. So we don't have to land to do our mission. It would be great if we did, but we're going to Venus.
All right. Next one, I will also start with Dr. Smrekar, but you may well want to join in, Dr. Garvin. This is from @RedClicks on Twitter, who's asking, what really inspired NASA to return back to Venus? It is really exciting. At the same time, it's very challenging to accomplish this hottest planet destination. What are your thoughts? Why do you think we're inspired to go back to Venus?
Well, so many reasons, but we heard from the interview with Senator Nelson and Dr. Zurbuchen about the different atmospheres and the different surface temperatures for Venus and Mars. And so, Earth is kind of like the Goldilocks planet. It's just right, and Mars is cold and barren today. Venus is super hot, and Earth is just right. So, we've learned so much in the past decades about Mars. And of course, we're learning new things about the Earth all the time. So we really need new data for Venus to be able to understand what it is that makes Earth unique. Why is it the only place we know of yet that has life? Why is it so supremely habitable today? We need data from Venus to be able to answer this mystery and look for similarly habitable planets around other stars.
Well, if I may add, Karen, I would say, and agree 100 million% with Sue, but it's because it's time, folks. If we ignore our sister next door, what do you think that says? I mean, I guess we ignore our neighbors sometimes, but in this case, we don't want to, because she has so much to tell us. And yes, she's hard, but the engineers of planet Earth, those women and men that make things possible, that we just talk about all the time, they're going to let us do Venus right, so we can use what she's trying to tell us. She's been trying, literally wailing at us over the last 30, 40 years to come home, to come back. And there's Venus, as you can see from Magellan, a beautiful view. We need to go back because the time is right. We have the tools, we have the people, we have the models, we have the interest. And wouldn't it be horrible if we didn't know our sister next door and started to see this plethora of exovenuses that Dr. Zurbuchen was talking about? There may be dozens of them that we see with our James Webb Telescope. We have to measure our Venus to understand those Venuses. That's what it's all about.
Thank you. The next question is from William on Facebook, who asks, what materials will be used to keep the spacecraft from melting? That's probably a Da Vinci question for starters, but Veritas may well have its own thermal constraints to work with.
Well, Venus is hot and hard, as good question, but we're building, our spacecraft is about a meter diameter, spherical or hemispherical titanium pressure vessel. It's like the bathyscapes that carry great ocean explorers. You can see the Da Vinci probe there. It's about 3.5 feet across. It has spin vanes, so we can take beautiful images all the way down. It's made of titanium, and inside we use a phase change material to keep the temperature just right for those exquisite instruments that measure the chemistry. And we have other techniques, special kind of seals that allow just the atmosphere in when we attempt to make those ingests of atmosphere, and at other times don't let it in. So this technology, it's worked before for our colleagues in Russia. We use
Great, thank you so much. We're still going. Remember, you can send in your questions to @AskNASA. Sorry, that's hashtag AskNASA. Next up, we have a question from @NickBE24 on Twitter, who asks, what data are you hoping to collect through these missions? We can do Dr. Smrekar again first, and then Dr. Garvin.
We are excited to be collecting a number of different data sets: global topography, global radar images. We will get data from our spectrometer about the surface composition. We use that data to look for recent volcanism. We can get thermal signature of active volcanism. We will be looking for gases coming from volcanoes, and water in particular given off by active volcanoes. So, and then lastly, we take gravity data, which tells us about the core, about the mantle. And I just want to say we're also taking data to measure active deformation on the surface. So we have a bunch of different ways to see the surface.
Well, on DaVinci Plus, our job is to make hundreds of exquisite chemical measurements. Again, as I said, an order of magnitude better than ever made before, and hundreds of times. We will make a complete transect of the atmospheric chemistry. We will sniff the inert noble gases and look at their isotopic ratios. That's a big word. Sounds like it's out of jeopardy, but it's not. It's something that allows us to piece together the past history of Venus. Why was atmosphere changed and oceans lost and volcanoes erupting? We can read all that through the measurements we make in the atmosphere from our chemistry measurements. We'll also take hundreds of descent images through our surface port right at the bottom, sapphire window. Will let us see the surface bright and sharp, just like the landings on Mars, only we'll do them in 3D with composition. So we'll be able to measure what the rocks are like locally to compare to Sue's measurements to the global ones from Veritas. And in the mountains of Alpha, we're thinking these could be an ancient continent with evolved rocks like you'd find in the mountains of New England or the Canadian Shield. So we'll make those measurements and pressure, temperature, accelerations all the way down. It'll be a wild ride. And that data will be a boundary condition for scientists for generations to come.
Thank you so much. We have a lot more questions coming in from social media and online, but all of you sending your questions are not the only ones excited about these new solar system missions. So we're going to hear from some other Veritas and DaVinci Plus mission team members.
NASA is returning to Venus after 30 years.
We are going back to Venus, and our team of managers, engineers, scientists, technicians, and instrument developers are ready.
I was extremely excited to get to compete with other professionals to try and put a new mission around Venus.
Hi everybody, and good morning. I'm in an environment right now that is as different from Venus as you can possibly be. We have water, we've got ice, we have trees.
Venus is one of the most enigmatic worlds that we know of. We have so many unanswered questions about the planet next door.
How did Venus form? Did it have oceans? Where did the water go?
How Earth and Venus became so different. What makes a rocky planet become habitable and what makes it not?
What ancient climate may be preserved in the rock record? These are the compelling questions that drive me to study Venus.
I am passionate about Venus because it's been a puzzle that has confounded us for so many decades.
Venus promises those answers.
We're going deep into the atmosphere, learning about the atmosphere. We're going into orbit to get some long-term images, and this should be a fantastic mission.
I also, as a geologist, I'm anxious to see the surface of Venus with my own eyes, as it were.
I imagine what it is to be in the cloud of Venus, to travel through the transparent hot atmosphere below, and especially the environment near the surface where the air is so thick that in some way we are between a gas and a liquid.
In my wildest dreams, we're going to find a Venus that is even more volcanically active than what we observe on Earth today.
The secrets of Venus' past habitability will allow us to understand the evolution of Earth-sized planets around other stars.
I am very inspired and very happy to continue in the business of exploration, but also the business of inspiration.
We're looking forward to bringing the scientific community and the public along with us on our adventure.
This is a really exciting mission, and I am so proud to be part of it.
I can't wait for the data from DaVinci.
Working with a beautiful spacecraft with clever mission design and state-of-the-art instruments, and getting to making that happen, it would be tremendous fun, and looking forward to it. Go Veritas.
And go DaVinci Plus.
It is so great to see all the excitement and enthusiasm around these new missions. Speaking of excitement and enthusiasm, let's go back to the questions from all of you at home, sending them in. We have Canal A on YouTube who asks, will there be new technology on the missions to Venus that hasn't actually been invented yet? I'll toss to either of you.
Well, I can just say the technology of encapsulating the next generation kind of instruments we're flying to Venus, the kind that are operating on Mars now in conditions that are a lot more clement, had to be invented for us to even have a chance at flying these missions. These are competitively selected missions by Dr. Zurbuchen and the colleagues at NASA. So we have to compete for the right and the chance to do that. And so the technologies we invent are invented now to go to Venus. And we hope we can test new technologies as part of our technology demonstration experiments to even extend that further. And we have one on DaVinci Plus to measure the hyperspectral composition of the upper clouds of Venus, to see what are the mystery absorbers like. This is the kind of future casting we want to do at NASA that's just emblematic of who we are.
Yeah, I mean, we have another technology demonstration on Veritas. It's called a Deep Space Atomic Clock, and it is incredibly accurate. And by bringing that new technology development along, we can help improve our ability to measure the motion of our spacecraft and use that to sense the interior of the planet, to sense the gravity field. And it'll help future missions as well to be able to provide even better data for the interior of perhaps icy moons or other bodies where they can fly the Deep Space Atomic Clock in the future. And Veritas has a lot of excess launch mass, so it's entirely possible that NASA will decide to add another payload on that's being developed as we speak and maybe selected in future competitions. So stay tuned. We'll see what we actually launch with.
Great. Zero Shuki on YouTube asks, how are you going to keep the spacecraft up and running as long as possible since most die so fast? I'm going to tweak this slightly to add just about how long each mission is expected to the lifetime of each mission. But I think it's a starter question for DaVinci with going down onto the surface.
Well, our mission is a little over 2.5 years. We actually launch and fly by Venus twice to collect special atmospheric remote sensing data. We're all about the atmosphere. We think that's the history book of Venus that we want to read. And so we'll make these maps of cloud motions. We'll look at the atmosphere as we look at that of Earth. You can see the Earth here as we launch to Venus. So we're very excited about that. But then our final mission, we release our probe, and you can see us being released on our trans-Venus injection after we launch. But it'll take us about 6 months to get to Venus. We'll fly by Venus twice, and then going around the sun, we'll come back and we'll release our probe 2 days out. And then our probe spacecraft, again, in an aeroshell, will fly through the atmosphere for about an hour and reach the surface, landing at about a speed of maybe 20, 25 miles an hour. And during that time, we'll collect thousands of data sets of a new type: chemistry, imaging, composition, pressure, temperature, see the lower surface of Venus for the first time in this new way. And so the overall probe mission will be about an hour. If we survive in the surface, we may have another couple of tens of minutes, and then our spacecraft will play all that data back. So that's our mission lifetime.
And for Veritas, we get to Venus very rapidly, in about 6 months. And then we spend quite a bit of time going from a big orbit that goes out, 10,000 kilometers, and then bringing that orbit down slowly to being just a few hundred miles above the surface. So we actually use our solar panels to effectively act like drag flaps. You have a spoiler in the back of a racing car. Well, we use our solar panels instead, and we dip gently into the atmosphere, and it slows us down over the course of about a year. And in that time, we get into the precise orbit we need to be in to get the best performance out of our instruments. So, after about 2 years, we're ready to start taking our science data, and we spend about 3.5 years acquiring science data, mapping in a series of global passes around the planet.
Thank you so much. The next one up is a DaVinci question. John Spellman on YouTube asks, will DaVinci Plus be able to detect phosphine molecules? What would it mean for future missions if phosphine was actually discovered by DaVinci?
So first, DaVinci has 2 analytical chemistry experiments. One can detect phosphine throughout the entire atmosphere, especially from the lower clouds all the way to the surface, where no species with phosphorus have been detected. So we will be looking for that with exquisite detail, like the measurements being made on Mars now with our instrument. We also have an instrument that's a very special one that uses lasers and scattering that can measure lots of great species, and we can adapt that instrument by adding a new channel which is an option that we'll be pursuing in the next couple of years, to specifically measure the phosphine. That's such an exciting possibility for Venus. The bigger point, though, is we will measure the chemical context of all those interesting trace gases. Phosphine, which smells like swamp gas, but other ones that might be equally interesting that we haven't even discovered yet. And by producing that context, we can start to think about Venus as an astrobiological target. So it's not just phosphine, it's all of the context of the chemistry of this rich atmosphere that could have had a habitable cloud deck at one point in its past or not. But we need the context to understand that possibility. That's how the astrobiology community has recommended we work, and that's what we're going to do with DaVinci Plus.
Thank you. The next one is a volcanology question, so I'm going to toss this one to Dr. Smrekar. Srivatsa M on YouTube asks a speculative question about Earth. If all the volcanoes on Earth started erupting at once, could that turn Earth to look into something like Venus in just a couple of decades?
It would
That's
take
a hard one.
a lot more. Yeah, and I will have to draw on some conclusions that I'll put together as we speak. But there are about a couple dozen active volcanoes on Venus, and there are many on Earth. Pardon me, and there are many more that haven't erupted recently. So if we take all of those and put them together, we would certainly have a very big impact on our climate, and we would feel that right away. But it would not turn us into a Venus. That would take probably hundreds of millions of years before you would get to such an extreme point as Venus is. And really, the major difference between the climate of Earth and Venus is that on Earth, because we still have our oceans, the CO2, the carbon dioxide, is locked up in our rocks, in our carbonate rocks. That carbonate gas dissolved in the ocean and it precipitated out. It just sank to the bottom and created these carbonate rocks. And so, unless we release all of that carbon dioxide back into the atmosphere, we'll never become like Venus.
Good to know. All right.
For that fate, we have other things to worry about, but we won't get all the way to being a planet like Venus.
All right, next question. Lou on Facebook asks, is it true that Venus's atmosphere smells like rotten eggs? Who wants to take that one?
Well, I can give a stab, and Sue can obviously finish. So rotten eggs, of course, is an acquired smell based on gases, compounds that involve hydrogen and sulfur. We'll be able to measure those. But however, most of the atmosphere of Venus is made of carbon dioxide with nitrogen and argon and other inert gases. So a portion of the atmosphere in the clouds you just saw is where we expect to find those special sulfur and hydrogen compounds. And that constitutes this really thick cloud deck that is very difficult to see through, needing instruments like Sue has. But we'll be sniffing those with instruments, not human noses, to measure what they're made of and tell you specifically, would they smell like rotten eggs or swamp gas or other things that would be very exciting to smell. And I think we'll connect the smells of humanity to the measurements of Venus when we fly our DaVinci Plus probe.
Well, I will leave it at that. The next question is Caden Colbath on YouTube, who asks, how long does it take to get to Venus? Dr. Smrekar mentioned that. Why don't we go to you for this one?
Sure. Well, it depends on how close you are to Venus when you launch, but we have different possible trajectories that would get us there from anywhere as short as 4 months to as long as 9 months. But we're hoping for a sweet spot around 6 months to get there.
All right, I'm going to add on a slight addition to that question from @FutureStarman on Twitter, who's also asking how long until the missions are ready to launch.
Well, we could be as ready as early as 26. NASA has asked us to be ready to launch in 28. That works best for their phasing of all of their various missions. So that's our goal at the moment.
Right. NASA's dictated launch scenarios for us based on funding profiles, which we're grateful to have. And so our missions are scheduled for the 28 to 2030 timeframe to reach Venus. And so That's going to be a great time to go to Venus. James Webb will be flying. We'll be seeing exovenuses. Maybe they'll look like the Venus we see here from Magellan. So we can't wait. Sooner would be better, but we'll take anything.
All right, tell us a little bit more about Venus. We're getting some good questions about the planet itself. Soumya on Facebook asks, does Venus have gravity?
Well, I can take that one. We're going to measure the gravity field of Venus very precisely. And absolutely, it has gravity. It's, sorry, I keep going the wrong direction here. But I need gravity to hold me in place. Yeah, so we are going to measure the gravity. It is just slightly less than that of the Earth because it is a slightly smaller planet. So the gravity at the surface is about 10% less than on Earth.
All right, this one will be for you as well, Dr. Smrekar. Robert on Facebook asks, is there evidence that oceans existed or are they theoretical? Actually, I take it back. I think either of you can answer that, and Da Vinci is looking for oceans. So I may toss this one to Dr. Garvin. I got that backwards.
Well, Karen, I can take a stab, and I think Sue should as well. So the evidence of oceans is recorded in the measurements that were made from spacecraft in the late 70s that involved measuring what are called the isotopes of hydrogen. And that critical ratio of regular hydrogen and heavy hydrogen gives us an insight on how much water bound in hydrogen molecules was present. And we made that measurement thanks to Pioneer Venus Large Probe. And since then, high atmospheric measurements have been made by the Venus Express mission. And they show a possibility of very grand oceans. But the real exciting thing is, like you can see here, perhaps for billions of years through Venus history, the exciting thing is that new atmospheric climate models developed by the community around the world have shown us the possibility that if Venus works the way we think, and again, as Sue said, there may be myths about what we think until we measure more, but if it does, Venus could have harbored oceans for 3.5 billion years. What Da Vinci Plus will do is measure that ratio at exquisite precision 10 times through the atmosphere, from above the clouds all the way to the near surface. And that will set the record straight. Did it have big oceans? Did it? When were they lost? How were they lost? Why were they lost? Those are key questions we can ask through the chemical measurements that we will make in context with Da Vinci Plus.
Right, and Veritas will take another slice at that question. We are looking for evidence of analogs of Earth's continents. On Earth, the continents that we live on formed when huge amounts of oceanic crust, the basaltic crust, iron-rich crust, melted in the presence of water. And so with our instruments, we're going to determine if these giant plateaus on Venus are in fact just like Earth's continents and are thus telling us about the history of past water, that crust melted in the presence of water and shows us that there's still this history of water locked in the rock record at the surface.
All right, thank you. Next question is from Shriyanash Singh on YouTube, who asked another speculative question that we cannot specifically answer for NASA, but it says, will far future Venus missions include a sample return system from Venus? And of course, we cannot predict what NASA will choose down the road, but if you know of anybody thinking about it or what samples might tell us, I'd love to hear.
Well,
and if we don't even think about it now, we can move on.
I was just going to say, Sue did a great study for a Venus sample return mission, so I think she could actually tell us how we might do that.
Well, there are a number of sample return mission studies in work, and so it's super challenging. We're looking at trying to do that for Mars right now, and perhaps the biggest challenge is getting that surface, that sample to back to the Earth, is getting it off of the surface of Venus. So there are a lot of studies underway to begin to address that question. And I'm sure we're going to learn a lot in the coming decades from the process of returning samples for Mars. So it's in the pipeline in terms of developing the approach.
All right, that's exciting. Thank you. Matthew Taylor on YouTube asks, how do you think the planetary science gleaned from these missions could benefit human habitation on the Moon, Mars, and beyond? I'll go to Dr. Garvin first, and Dr. Smrekar, please join in if you have other thoughts.
Well, as we explore, we learn how to extend the limits of our performance. So at Venus, we have challenges as we go into the atmosphere, and those technologies can produce new thermal regulation systems, like the heat shields that got the Apollo astronauts back from the moon, developed that were then used by the Viking project to get into the atmosphere of Mars to land two exquisite landers. That feed forward is typical of our missions, and we want to get the women and robots and next generation to the moon and of course to Mars. So what we do in all of our planetary exploration is build the piece parts, and we build them together in a mosaic of future capabilities that we can then use. And some of them extend to IT solutions. So we need to be able to process data, especially seeing things in new ways with camera systems and systems that measure chemistry. The environmental health of people will depend on some of the kind of instruments that we'll be flying into the atmosphere of Venus, for example. And we need that to keep the crews alive as they live on the moon and do their work through the Artemis program and the Artemis base camp. So there's always a feed forward, and we at NASA, I think, do a good job about capitalizing on that. So that's my 1 cent. I'm sure Sue will have better ones.
No, I think you said it well. Really, every technology that we develop and every mission that we build and send out into outer space, helps us learn lessons of taking the next steps. So I think I have nothing further to add.
Great. Well, we're talking about the moon and Mars. Let's bring it back down to Earth. At Planthony C on Twitter asks, what sort of context will these two new missions provide for climate data collected by the upcoming NASA Earth System Observatory missions? We can tweak that to at least how does it help us understand climate if you don't know about the ESO mission specifically.
Well, I can take a quick stab. So the ESO mission, starting with NISAR and other missions like Clario and PACE and on out, build on the climate history of our own planet, where we have an exquisite capability of modeling and predicting, and it's taking off. It's so exciting. And we apply that to worlds like Venus and try to backcast. And so by making the kind of measurements that both DaVinci Plus and Veritas will be making at Venus, we build the boundary conditions to cast those models for Venus. Today, those models are limited. We don't have adequate data. We don't even know the temperature lapse rate from below the clouds to the surface well enough to constrain some models. Well, how does it change? Well, we need that for Earth, of course, and we need the history of water. We need all these features. We need the topography of Venus as a primary boundary condition. We need to know why its very slow rotation will affect those kind of climate models. So we will learn from these missions and apply them, the lessons we learned for Venus, apply them to Earth. The same way we learned from Mars, and its very interesting topsy-turvy climate history has also shed light on the history of climate on Earth. So there are always these connections as we go somewhere and apply it back home, in my view.
Yeah, there are just so many. Yeah, if I could just add, there's so many parallels between Venus and Earth. The people who discovered the ozone hole on the Earth that has a major effect on Earth's climate were actually people who were studying the chemistry of Venus's atmosphere, and they decided to go and look for ozone, and as a process, and in that process discovered this ozone hole. And similarly, people who have proposed using sulfur to try to help slow down climate change on the Earth. People studying the climate on Venus said, look, that's really not going to work because we see on Venus the breakdown of sulfur at the top of the atmosphere. So, there are parallels to the present day climate, but there are also parallels to the long-term climate. We think that Venus and Earth have similar amounts of carbon dioxide altogether, but on Venus, that carbon dioxide is in the atmosphere, making it this incredible, runaway greenhouse that makes it 900 degrees at the surface. Whereas on Earth, that same carbon dioxide is locked up in the rock record. And by studying processes of subduction, where the crust goes from the surface back into the mantle, that's effectively sequestering carbon dioxide, right? And so we're going to learn how that process may have started on the Earth. So, we could talk for a long time, but there are just so many parallels between Venus and Earth, and it's all essential to really understanding both the present day and long-term evolution of the climate.
All right, we are finishing up here with some of our last questions. At David Johnson VG on Twitter asks, when did you first find your own interest in solar system exploration? Let's do Dr. Smrekar first and then Dr. Garvin.
I was certainly a kid when Apollo astronauts were landing on the moon, and of course that was very mind-blowing and inspiring. But I think I did not completely imagine planetary geology, geophysics as a career until I got to college, and it was really there that I learned I could study how processes work on other planets, and I was completely hooked. It was just a fascinating idea of being able to do that. And so that led me to doing things like studying volcanoes on Hawaii as a means to learn about volcanoes on Earth.
Well, Karen, I like Sue, my mother said I was hooked at birth, but I don't know what that means, so we can all reflect on that. But I was looking up at the moon as a little kid and saying, why aren't we there? And my parents said, well, it's a long trip and, gas prices, not going to work. But like Sue, I was enthralled by Apollo and saw the Apollo 11 landings as a young kid and couldn't believe it. I was able to then transfer that through my college experience in high school to visit places that reminded me of Venus. Here, the impact site Zhamanshine in Kazakhstan, the most recent big impact. And searching for Venus on Earth has always been one of my passions. Two of my advisors in college and in grad school told me, you better look at Venus, Jim, even though I was funded by Mars. So I basically reconstructed my whole graduate school career to study Venus and was able to participate in the Soviet missions to Venus, like the Venera 13 lander here that lasted 127 minutes. This is its sister sitting in Moscow. Here we are thinking about Venus 15 years ago when we started the Sojourn to become a mission like Da Vinci Plus. We were very excited about actually making it work. And here, the Eye of Venus with me, looking through the sapphire window that we now look forward to flying to Venus. So I was always dazzled, and I don't think I can ever let go. I can't actually stop working on it. So my family often tell me that. So it's science doesn't sleep. I can attest to that.
Thank you so much. That is all the time we have for today. And I really want to thank you both for joining us.
Well, thank you so much for having us.
And if you want more information on Veritas or Da Vinci, you can visit go.nasa.gov/new-Venus-missions. And you can also follow us on @NASA Solar System on Facebook, Twitter, and Instagram. Until next time, I'm Karen Fox.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
I think it's just an incredible honor every day when I wake up that I'm working for NASA. So I'm going to just lay my nerd cards out on the table. What I'm really looking forward to is just seeing all the new and different experiments. It's been 4 years since I've been there. So, I'm telling the program guys, give me more experiments, more experiments. I'm looking forward to being as productive as we possibly can.
It's really fun to be up here. You get to be all kinds of scientists at once.
It's actually really phenomenal. It's a world-class laboratory, and it's an absolutely packed one. I think it's like taking an how to do lab work.
It took about 10 gentle shakes with this kind of motion to get full RNA reader distribution and none of those mixing lines. Copy that, and we like what you saw and are doing. This is why we can't automate things, and we need humans.
I think one of the best things about being in space is that it surprises you every time. You think you know what it's going to be like up here, and then it's just completely different.
In space, I get to see everything from physics to material science. To biology. It's just this incredible sense of wonder and joy.
We're increasing our complexities double time today. Appreciate the patience. This is awesome.
It's no problem. I flew my crewmate Ike around on the robotic arm on an EVA not that many days ago, so I sure understand what it takes to do the setup in the robotic commanding. I feel ya.
We're trying to take a census of which microbes are on space station. So we're working on a comprehensive sequence-based map of the space station. We're taking about 1,000 samples total. And so I'm very carefully swabbing all of the modules. Everybody floats by and says, Kate, are you still swabbing? And I'm like, yep, 1,000 samples is a lot.
We trust you that you're doing your very, very best, and we appreciate it.
This is our home. We even see it on videos sometimes when we go back, and I look at it and I think, wow, I feel like this is my home. But certainly the planet is home as well, and I'm going to always try to keep that in the forefront of my mind and appreciate that.
Kate, we thank you for continuing to push space science through your work on board and through all you do to socialize and emphasize the importance of molecular biology in space.
It's really, really, really fun to be at the pointy end of this spear here and to get a chance to do the sequencing in space. So I'm very excited about this, and I can't wait until we're multiplexing 96 well plates and swabbing everything on the space station.
That's where we're headed next.
There's a lot going on up here, and I really do think that science is an incredible career, whether you're doing it in space or on the ground. If people are interested in this, the pleasure and the gratification of being a scientist every day, it's truly amazing to get up and discover new things.
Hello, and welcome back to Pass the Torque. I'm your host, Katie Caudry. This season, we've learned about all things OSAM, or On-Orbit Servicing, Assembly, and Manufacturing, and today we're going to learn about research and development from Dr. Crystal Johnson. Don't forget, you can leave a question for Dr. Johnson in the comments below for a chance to have them answered later this week. Let's go ahead and jump in with the first question. What is your role at NASA? Can you explain what you do?
I'm Crystal Johnson. I'm the Deputy Center Director for Technology and Research Investments at Goddard Space Flight Center. And what I do is I shape the missions of the future in astrophysics, earth science, heliophysics, and planetary science. And then I'm responsible for making sure that we have a really solid technology portfolio that is matured in time. All these technologies have to be developed and matured in time for us to be able to infuse into those amazing missions of the future.
Can you tell us about your background?
My background, I started in laser design and development at Langley Research Center. So I was developing a chromium lysaf material. We were looking for new materials that we could develop into lasers, and these lasers for remote sensing of the atmosphere. And so that was the start of my career, but I went from that to being the deputy for our electro-optics and controls branch. And then I was responsible for all of the laser activities going on at Langley Research Center. We had multiple projects going on, but I was the one that interfaced with headquarters to get the funding for all those different projects, and then distributing the money across the different organizations at Langley. Then I had a wonderful opportunity to go to NASA headquarters. I was the associate director for all exploratory missions. So any mission where you're probing the Earth to answer a specific question were my responsibility. So I did a lot of international work with lots of different countries, spent a lot of time at Jet Propulsion Laboratory, a lot of time at Goddard, looking at all the projects that were under my responsibility. And then we had the Columbia accident, and we knew that we were doing a horrible job. We had been told by the Accident Investigation Board that NASA was doing a horrible job overseeing the engineering for our agency because it was just an advisor position and there were 5 people on his staff. So they asked to stand up this new Office of the Chief Engineer. The Chief Engineer at that time asked me to come up and help him stand up a whole new Office of the Chief Engineer. So I did that, and I became the Deputy Chief Engineer at NASA.
What does the research and development process look like at Goddard? Can you walk us through a project from start to finish?
Yeah, so research and development, there's no research and development project that's exactly the same. Everything depends upon the state of the technology that you're trying to develop. For me, when I was at Langley Research Center, and the way that it is for many at Goddard, you actually start going in the laboratory. You have this idea that you want to test out. And for me, I was trying to come up with these new crystals that we could actually formulate into a laser material. So you go in the laboratory, you get the material fabricated, or whatever device it is you're trying to create, you piece together a laboratory version of it. Then you test it out in the lab to see if it works. Then from there, you can actually start developing a protoflight type, one that is very close to a flight version of it, but not necessarily flight, because flight requires you to have specific soldering, specific parts, specific testing, all of that. So you develop the next to flight version of it. And for us, we would do it piecewise. So you do a laboratory version, and then we do a version that we could fly in an aircraft. So you could actually test out the capability, make sure that it measures exactly what you want it to measure in a very close to space kind of environment. But for us, it was just on an ER2 plane. So for Earth science measurements, you can fly it in an aircraft first and see if it's going to make the kind of measurements that you'd like for it to make. Once you get all of the bugs worked out of that, then you prepare for a space qualified version of that. And then by that time, you think it's pretty close to being pretty sure, then it's going to perform the way that you want it to perform. So it is a stepwise process that's required. One of the few places anywhere where you have complete end-to-end capability, all the way from coming up with an idea, crazy idea,
development.
Research and development is always, you start with a concept, and the end goal is always to be able to apply it to make the actual final measurement. So whether you're coming up with a new detector that you want to sense, exoplanets, a long way away, the ultimate goal is to be able to get that device measuring it and to make that measurement and be able to have the data the data that comes from that measurement come back and inform everybody. So at Goddard Space Flight Center, we are a majority science center. And for us, the most important thing is for us to be able to get the science data back down so that we can apply it to our knowledge base to improve on whatever knowledge we have. So the technology development, there have been lots of debates about when you do technology development and getting funding as a part of a project for technology development. But one of the lessons that we've learned over many, many years is that it pays significantly for you to develop the technologies before infusing them into actual missions. Because if you run into problems, the cost for the mission goes up and up and up, and you never know when, you're actually going to get your arms around it and fix the problem. So the technology development is a very important part for us as we're developing the missions for the future. But then once we get the technology developed, it's not a matter of just infusing it into that one mission and being done with it. For us, it's really important for us to transfer that technology to industry, for them to be able to commercialize it and be able to fuel the economy and make more from that technology than we even envisioned when we first developed it. Many times we find that you start with one particular application in mind, but then the benefits of that particular technology can go into a different field, and you can make a revolutionary change to the way that they're doing something in a whole different field. So that's exciting. That's one of the real exciting parts of technology development.
How does Goddard decide what projects to pursue? What is Goddard's long-term strategy?
Yeah, so Goddard is a science center. And so the great thing about science, we are one of the only organizations that has a full capability and a full deep bench in all 4 science divisions. And so that's astrophysics, earth science, heliophysics, and planetary science. We are the largest portfolio anywhere for heliophysics, studying the sun. And so the great thing about science is we have these decadal studies, and the decadal studies are not even done by NASA. It's an independent look involving experts from all over the world, and especially, involving academia, involving private industry, involving some NASA employees, but they kind of take a look at what are the next measurements that need to be made, not just today, but way down the road in the future. And so when they come up with their decadal priorities, we take those decadal priorities and we think about, all right, if they say we need to make this measurement, we think we can make that measurement by using this kind of instrument, using this kind of platform, and whatever else. And so we build our missions based upon the priorities that come out of those decadal studies. And so you can make a measurement multiple ways. And because we are one of the largest groups that can perform all of these different things, we have partners that come to us from academia, from private industry that want to partner with us. So we end up having multiple proposals for one target area. Let's just say we want to go to, Europa to make some measurements in Europa. There may be a couple of different people that come to us with an idea of measurements that can be made on Europa. And that's if Europa is a priority, we'll say, for that comes from the decadal. We really have to kind of look at several different factors that go into us making a decision which of those we actually choose to work on and that we choose to put a proposal forward on. A lot of it depends on team members, who's a part of that team, what kind of measurement or what instruments are they using to make that measurement? What is the total concept? How feasible is that concept? For that concept, how many technologies will be at a technology readiness level of a 6 before you even get to PDR? And there's so many, there are like 100 different factors that you could consider. But we have a way of looking at all of those different factors, putting them together, and determining which ones we think have the highest probability of being successful in the review process at NASA headquarters. And we go with those. And so since we have so many scientists at Goddard, we don't get into the business of saying yours is going to win and yours is going to lose, because we're not the selecting official. The best thing that we can do is put our best foot forward with the things that we think have the highest probability of being successful. And whatever the target is that SMD, our Science Mission Directorate, feels are the highest priorities, those are the ones he's going to pick, as long as they're technically feasible and they're low risk, relatively low risk missions. And so there are a lot of different factors that go into it, as I said. Yeah, I mean, we do a lot of that kind of work here. So if you think about the spacecraft that have flown right now, when you turn on the news today and you look at the weather, those weather forecasts that you get, NASA has developed, or Goddard Space Flight Center has developed all of those platforms that NOAA uses to be able to tell us what the weather is. Not a single one of those have been done on the domestic side. We are the ones that are doing those for NOAA. So every day when you turn on the TV, that's a great example of how we have been helping to improve the quality of life. You think about all of the data that's come down from the International Space Station, all of that's come right through Goddard Space Flight Center. That's a huge amount of data and a huge accomplishment for our center. And there's so many different things that we do on a day in and day out basis that are very, very exciting.
What are some cool things that Goddard does that people might not be aware of?
Well, I will say one of the coolest things that we have done is we have a search and rescue beacon that we have developed at Goddard Space Flight Center. I don't know if many people know about that, but that search and rescue beacon you can actually use the satellites to triangulate a single signal that comes from that search and rescue beacon, and we can find you wherever you are on this planet. That is an amazing capability. It's now being used to also help with the search and rescue capability for our astronauts. It's being used, it's saved hundreds of thousands of lives since we actually put it out. For people who go hiking and end up getting lost, they can use their little beacon to send us a signal, and we'll be able to find them. People can use them when they go out in boats on the water, and so many different applications. But that's probably one that most people weren't even aware that's happening right within the gates of Goddard.
What is an exciting technology that was developed at Goddard?
There's so many different technologies that we've developed at Goddard. The search and rescue beacon is my favorite, absolutely, because it is affecting lives every single day. And without it, so many people would be, they'd lose their lives. And so that is a very important technology. But we have the core flight system software as well. So when you're talking about command and data handling for spacecraft, we have developed a modular platform that you can actually make changes to one specific element of it. And it's open source software now. It's been offered to the public. And we're finding that companies that are building spacecraft are using Goddard's core flight system for all of their command and data handling capabilities. So you can make a change in one section, test it out on the platform, make changes to it without having to reboot the whole system and without having to start from scratch. So it's saving these companies tons of money. And every time we come up with a new mission, we've already got a system in place and something that has, you already know what the connections are for all of it. Saving money, saving requirements, and everything else. So that kind of software development that we have done has been top notch, and not just used by NASA and some of the companies that are providing spacecraft. Even other agencies, other space agencies are wanting to use our software.
What are you most looking forward to at NASA in the next few years?
I think, well, so one of the things that I'm really looking forward to, as I mentioned, is actually being able to see us put a woman on the surface of the moon. For us to be able to test out so many technologies and capabilities on the moon in preparation for us going to Mars, that is going to be amazing. And for us to be able to have a sustainable presence on the surface of the moon, where you're not just coming back and forth, but having people live on the surface, learning how to live on a whole different planet that's not in an International Space Station, this is going to be absolutely amazing. And just think of all the innovations that we have come up with just for us to be able to go from Earth to the International Space Station and back. With all of those developments and amazing technologies we've brought to bear, imagine what kind of new innovations there will be when we have to create something from nothing. We have to learn how to develop our own food and make sure we have clean drinking water and, make sure we have air that is going to be sustainable for us to be able to live, with. Those kind of things are amazing. For us to be able to go to the moon, we've got to create suits that can protect humans from the amount of radiation that they're going to experience on the journey. And it's a long journey going to Mars from Earth. And so there's so much that still has to be uncovered. And you think about the thousands and thousands of technologies we developed that are now improving the quality of Earth, the quality of life, like the jaws of life that we had to develop for the International Space Station, where you could actually cut metal with one person doing an extravehicular activity. They're going outside of the space station, and one person alone has to be able to cut metal with no gravity to help that. We came up with the jaws of life, and the jaws of life are being used now when people have these horrible accidents and their cars are mangled and people are trapped inside the car. They use the jaws of life to cut the roof off of the vehicle, and they can pull those people out. We've done things like even things that are not, as detrimental as something like, somebody trapped in a car. People like Speedo, the company Speedo, came to NASA and said, hey, you guys do a lot of drag and friction reduction in your wind tunnels. Could you help us reduce the drag for swimsuits? And we said, of course. And so we worked with them to develop a swimsuit that actually reduces friction and drag for the swimmers. And the first year that those swimsuits came out, they had 8 world records broken in the Olympics by people wearing our swimsuits. And so, I could tell you 1,000 of those, and we don't have time for me to tell you 50, because I could tell you 52. But there are so many technologies that we've developed because we had to. And just think of what we'll be able to do in the future.
What do you do for fun outside of NASA?
Well, my favorite thing to do outside of work is travel. I love to be able to go places that I've never been, experience cultures that are different from mine, and just meet people from different parts of the world. It's been very, very enlightening to kind of pick the brains of some people that have very different life experiences from mine, and it's very, very enriching for me. I will say my favorite place that I have been, I'll just say because it was just such a wild experience for me. I had a birthday, a big milestone birthday. I won't say which one it was, but 3 years ago, I had a major milestone birthday. And I said to my husband and my son, I want to do something I've never done before. I want to go someplace I've never gone before and just experience something really different. Well, my husband had to work, but my son and my brother decided, they were like, I'm in. Whatever you want to do, let's just go do it. So we bought airplane tickets, hopped on a plane, and went to Dubai. I had never been to Dubai before, and I was like, oh, I'd love to go there and just experience it. So we went. We had this excursion while we were there to do camel riding and do dune bashing. They call it dune bashing. So you're in one of those SUVs and you're holding on for dear life on the top, and you're jumping dunes in an SUV, going out into the desert in the middle of nowhere. So we go out and we're dune bashing, and then we go quite a ways further, and we ended up at this place where they entertain people. And so you do camel riding out there and all. So I went and hopped on a camel just so that I could take a picture, and the gentleman surprised me, and the camel stood up, and we're, walking on the camel riding at nighttime, which is scary to me because I wasn't, camels are tall, much taller than horses. And so you're way up, you don't know what this camel is going to do. And I'm recording myself, the dancing and all of that, the belly dancer and the male dancer twirling around and all of that. So it was just a really neat experience and something cool to do for a birthday.
Thanks so much, Dr. Johnson. And thank you for tuning in to another episode of Pass the Torque. Don't forget to drop a question in the comments below for Dr. Johnson for a chance to have them answered later this week. We'll see you again next week for another brand new episode of Pass the Torque.
Hey, NASA astronaut Reed Wiseman.
Hey.
Do you think you have a few minutes to answer everything about living in space?
I got all the time in the world.
Awesome. Well, where are we?
We are in the Space Vehicle Mock-Up Facility. It's a gigantic building at the Johnson Space Center in Houston, Texas. And this is where astronauts spend the bulk of their time training for spaceflight.
Is this the window where you took all of those really cool pictures of Earth?
This is the cupola. It's a series of 7 windows that look down on the Earth.
Nice. How big is the International Space Station?
They say it's about the size of a 5-bedroom house. It's kind of hard for me to conceptualize. In reality, it's just really narrow and really long.
How long did you have to train before going to the ISS?
About 5 years.
And how many total days have you spent in space?
165.
What's the record?
Jeff Williams, he has the US record, 534 days in space, but Russian cosmonaut Gennady Padalka, almost 1,000.
Wow, what's a groundbreaking experiment that you completed aboard the ISS?
I survived.
I heard you age faster in space.
Maybe a little bit.
Is there a maximum height or age that you have to be to become an astronaut?
We used to have restrictions on that, but now it's pretty much come one, come all.
Is there Wi-Fi?
There is, but it's not as good as it is on Earth.
How do you get in contact with people on the ground?
We have space-to-ground communication systems. It's basically a radio or a walkie-talkie, and we just call on this and say hi to Houston.
Is there a delay?
Almost none.
How did you get to the station?
A rocket.
How long did it take for you to get from Earth to the space station?
Takes about 6 hours.
And how long did it take for you to get back?
Oh, that's a crazy ride. It's about 3 hours long.
Any jet lag?
Horrible jet lag.
How often do you get to talk to your family?
Get to talk to them. Once a week.
Ever prank call anyone?
Of course you prank call people.
Ever get homesick?
Yeah, you get homesick a little bit.
So are the beds comfy?
There are no beds.
I heard you have to be strapped to a wall.
You do?
Are you claustrophobic?
A little bit.
What else can you do in your room besides sleep?
You can read, watch TV, do some work, whatever you want.
Do you have a bedtime?
Everybody has a bedtime.
Do you have alarm clocks?
I use my watch.
How many crew members do you have?
It was me and 5 others.
Were there any language barriers?
Doc and Yeshna, of course there were language barriers.
Ever get sick of your roommates?
No, you never get sick of your roommates.
What did you do in your free time?
Oh, you look out the window.
What's a typical breakfast aboard the space station?
It was very much like a breakfast on Earth, so I liked eggs, occasional oatmeal, maybe
away.
bungee cords.
So do you burn the same amount of calories as you do on Earth?
I think you burn a little bit more because your brain is always active.
I heard that in microgravity, sweat sticks to you.
It does. If you have hair, it kind of builds up in your hair and you get this big sweat bubble on your head.
How do you shower?
We have soap impregnated towels.
How do you pee in space?
Ooh. We have a funnel.
Where does your pee go after you flush?
A little bit of processing and then right back into the drinking water.
How do you pee in a spacesuit?
We have a diaper.
How much water do you have to drink each day?
You drink just about the same that you would on Earth.
Do you ever run out of anything?
Free time.
How do you get more supplies?
We have cargo ships. We have great companies like SpaceX, Orbital. We have Russian resupply vehicles and also Japanese HTV spacecraft.
What'd you miss most on Earth?
Oh, my wife and kids.
What personal items did you take with you?
Photos of my wife and kids.
Did you bring any space souvenirs home?
You always have to bring souvenirs home for your kids.
So I have to ask, what's your favorite planet?
Oh, it used to be Saturn until I saw Earth from space.
And if you were to travel anywhere in the solar system, where would you go?
I work at NASA. We all want to go to Mars.
Does the space station ever get too hot or too cold?
Oh, we keep it a balmy 72 all year round.
Nice. How about the temperature of space?
Plus 200 F to minus 200 F.
What about the temperature inside the spacesuit?
It's actually pretty warm, pretty nice, pretty comfortable because there's many layers of thermal protection.
How much does the spacesuit weigh?
Oh, it's really heavy. I think it's about 300 pounds.
How do you do your laundry?
We throw it out.
Do you have to clean the spacesuits?
Of course you got to clean the spacesuits, especially after a spacewalk.
How long does it take for you to put on a spacesuit?
About 45 minutes.
Can you put it on by yourself?
If you're in a pinch, you can put it on by yourself.
How long does a spacewalk normally take?
We train for about 6.5 hours.
And what's the max amount of time a spacewalk can last?
The maximum is about 9 hours. I think 8 hours and 54 minutes is our record.
How's the view?
Awesome.
What's the hardest thing about a spacewalk?
Just knowing that you're outside, and if you mess anything up, you've destroyed a $100 billion spacecraft.
And what's the most rewarding?
Coming back.
Sounds awesome. Well, I'm sure there are a lot more questions, but I know you're busy, so we'll save those for another time.
Sounds good.
Awesome. Thanks. Have a good one.
See ya.
as species of explorers. I'm sure you remember the first time you felt it, that sense of awe and sense of universal wonder. As a child, you looked up and saw the night sky in all its silent glory. It covered everything around you and was ever present. It was straight out beautiful, and you knew that it was important. You can look at it again the next night, or travel elsewhere, and it was still there, and still beautiful, and still important. As we grow up, we keep looking at the sky, and perhaps there are two overarching thoughts that emerge. First and foremost, there's a sense of unity of all humankind, because even though there's many different people at various places on Earth, and they look at their sky at different times or from a slightly different angle, we all have the same sky that we're under, and the same stars and the same sun shine on us. We're under the same firmament, like a huge tent, and in that tent we are united in our most fundamental experience of science and united in our human condition. The second element, though, if you share that experience with a child, is also evident. What happens? The child starts asking questions. These questions are an incredibly important positive thing and reflect the innate curiosity about our experience in the universe. And here's the secret. If you try to address those questions, you never stop looking at the sky and you learn more and more about the sky. The sky does not become less interesting, but more interesting, not less beautiful, but more stunning to all of us. The insights we get from science and telescope and robotic explorers enrich our view of the world in ways that we could not have predicted. We learn, for example, that the sky is nothing like the calm experience it pretends to be when we first look at it. This appearance is merely because of the mismatch of timescales of the change of the universe and our own lifetime. But stars are constantly being born and go through evolutionary histories, and so often end in violent ends that are explosions that are seen throughout the entire universe. This is seen throughout, wherever we look. Many philosophers have thought about that experience of looking at the sky, that experience of exploration that underlies the questions, these childlike questions. But it's the words of a child that I'd like to repeat here, the words of a child from the Artemis generation. He says, curiosity, insight, spirit, opportunity, if you think about it, are all of the names of past Mars rovers. Those are qualities we possess as humans. We are always curious and seek opportunity. We have spirit and insight to explore the moon, Mars, and beyond. It is inspiring to hear a young person who is truly in the Artemis generation reflected about the motivation of much of science that is reflected in the qualities we have as humans. They are qualities that our children often understand better than we do as grown-ups, and qualities that motivate us to go forward. It is the childlike why questions that are at the heart of what we do. It is beautiful and motivating, and it pulls us forward. It not only changes what we know, but also how we think about ourselves and our place on Earth and the universe. I'm going to repeat one part. Curiosity, insight, spirit, opportunity. If you think about it, all of these names of past Mars rovers are qualities we possess as humans. We're always curious and seek opportunity. We have the spirit and insight to explore the moon, Mars, and beyond. Curiosity, spirit, and opportunities have brought us a long way in many different elements of our experience. We've been in space at the International Space Station for nearly 20 years, truly a marvel of international collaboration. We have learned about the views from space that many of those astronauts sent back. Just beautiful views of both our Earth coming together as one yet again, in unity, but also the aurora that are there at the edge of space and the upper atmosphere. We've learned about the changes of the Earth as observed from there and from other missions in orbit around our beautiful planet, the most beautiful planet we've ever seen, shaped by life itself. And we've learned about the other bodies in the solar system that are bizarre and so often in ways that we actually would have never predicted. There are questions still hidden in some of these data sets and new data sets that we're getting right now that we're only unraveling now. We've learned to look at the universe beyond that and look at our star, the sun, one of the most beautiful bodies yet again that we've yet observed, a variable star that's right there with us. We have learned a lot because of spirit and opportunity, but we have done it because of one more quality that we haven't talked about. We have done it because of perseverance. Because wherever there is exploration, wherever there is opportunity, wherever there is a pull forward, a question, the only way that relates to success is through perseverance. This year we're celebrating anniversaries for both the Hubble Space Telescope but also of Apollo 13. The Hubble Space Telescope is the most magnificent telescope ever built by humans. Conceived by leaders like Lyman Spitzer and Nancy Grace Roman, this telescope was built with very tough challenges, both technically but also programmatically. And when it finally was launched and was released by astronauts into space, and the doors opened and it took the first picture, there was a huge disappointment. The telescope had the wrong optics. It was short-sighted and needed to be fixed. A disaster to many, a disappointment to everybody. But through perseverance, Hubble not only became the most successful astrophysics mission to date, but also the best demonstration of the confluence of and mutual importance of science and human exploration. With over 150 terabytes of data, over 12,000 researchers worldwide are working and have produced over 15,000 publications and adding about 1,000 publications per year ever since. There has never been a space mission with the scientific impact. Remember that it was enabled by perseverance of those before us. Take Apollo 13 the same way. I'm sure everybody hoped that it would go as smoothly as Apollo 11 and Apollo 12 before that. But starting with the famous quote, Houston, we've had a problem. The Apollo spirit and sheer excellence of the integrated team on the ground and in space came together and brought Jim Lovell and his colleagues back safely. The trip was full of innovation, ambiguity, and fear. As the crew members worked with Jim Krenz and his ground troops to really work out solutions and innovate in ways that had never been done before. What initially looked like the most deadly disaster in the history of space travel turned into a story of leadership, of teamwork, and of unquestioned strength and success. It was perseverance, not giving up under pressure, and when challenged, that got Apollo 13 back home. And that helped us be safer and accomplish the missions better the next time. Perseverance has always been part of exploration, and it forever will be. As I mentioned before, we are having big plans for NASA and our commercial and international partners. Using our Artemis program, we're moving astronauts out of low Earth orbit and forward to the moon. We want to go back and land with the first woman and the next man on the surface of the moon. We want to establish a sustainable presence at the moon and then move forward to achieve a goal we've never achieved, is to get astronauts to Mars. There, we can explore the same terrains and the same environment that our robotic explorers, that are so aptly named, have explored before. Make no mistake, it will be hard to go to Mars or to the moon. It always is. Our next rover is aptly named because it takes perseverance to survive and go this distance in the rocket environment of Mars. And all of our human explorers face incredible challenges as well. I believe we were meant to explore, but doing so makes us first face some incredible obstacles. We can face those with science and with perseverance. Let me talk about two elements that are critical in this realm: managing the dangers of space weather and sending science to lead the way for humans. We live in the atmosphere of a star, a G-type star, like there are billions of them, both in this galaxy and elsewhere. A star that at its core is powered by nuclear fusion. Nuclear fusion that burns about 4 million tons of hydrogen every second and creates so much heat that heat, as it propagates out through the star, arrives at the surface of the sun and shapes it almost like the shape of a boiling pit, like an oil pan that you may see in your kitchen, turning over turbulent eddies. It's so hot, though, that much of the material, the solar material at the surface of the sun, is charged, and it's in a state of plasma. That state is very different than what we experience each and every day in our lives. But make no mistake, 99% of the entire universe in that shape of plasma. And in that state, that material is shaped not just by gas type of forces, but by electric forces, by magnetic forces that shape it and back react to the gas itself. That has a profound impact of how the sun appears. First of all, it makes it a variable star. A variable star in a timescale of about 11 years, when the sun goes to a more active, to a more quiet state. But on timescales of hours and minutes, where energy in these fields can immediately discharge and flare up with very high brightness to create solar flares. And those flares, of course, are part of another phenomenon, which is the ejection of large amounts of matter in so-called coronal mass ejections that get thrown into space all the way beyond the planets. What we don't observe so well, but is equally important, or perhaps even more important, is that these ejections are interacting with the plasma, the solar wind that was already there, and are accelerating particles to very, very high speeds, nearly the speed of light. Those particles are not really hitting us here on Earth because we have such a thick atmosphere and also a magnetic field. But as we're leaving Earth and low Earth orbit, we're exposed to those particles. Now here's the problem, though. Most of those particles from these storms and the entire space environment are shaped in the solar atmosphere in a place called the corona, and we've never really observed that space, and certainly not the forces that shape it and the particles really close to it. But that's changing right now. As the Parker Solar Probe is getting closer and closer to our star and making measurements ever so close to this corona, this atmosphere of our star, and we're already learning new ways of looking at space weather. In fact, we care so much about that in addition to the Parker Solar Probe, there's other missions that are out there that we're launching. The first one, by the way, built by the European Space Agency, Solar Orbiter, that will bring cameras to the inner solar system and also to higher latitude to look at the sun in new light from a different perspective to help us understand these connections. There's new observations from the ground, such as DKIST, but also in space, such as Punch and Sunrise, with both use small satellites to make observations of that near solar environment and its emissions in totally new ways, and join the campaign to really reveal that important source of space weather and the source of our entire space environment. This is done just in time because we want to be ready to support our astronauts with better predictions, and our cross-agency partners with better predictions to actually warn them when energetic particles of the type that I just talked about come their way. In fact, we care about it so much that as part of the Lunar Gateway, we are putting a package, a weather station, onto the Gateway and are making measurements, partner with the European Space Agency that put a whole radiation package on there, just the same way. Just like seafarers, depending on weather forecasts for their safe passage, spacefarers and our astronauts will depend on improved space weather forecasts that will come from these and other observations and model and theory development that we're working on right now. Again, it's curiosity, spirit, opportunity that pulls us forward. It is perseverance to these forces, to these challenges, that will make this an unquestioned success. And as we're going forward to the moon and to Mars, science leads the way. We're taking more risk. We're going faster with our robotic explorers than we're going with our human explorers. We're willing to take risk. We're trying to go faster and learn how to train, how to learn about the environments we're going into. We know that it will be challenging, not just for our robotic explorers, but also the human explorers that will follow. Mars, as we learned, is both stunning and a challenging target. The fact is that nearly 50% of all Mars missions ever attempted by humans have failed. And it's one of the most difficult and challenging things ever achieved. Just with Apollo 13 and many moments in our history, we keep our cameras on during these moments, even though we know deeply about the risks that we're going to undertake that moment. We seek to achieve this goal again as we launch our next Mars mission this July. The instruments that are part of this mission have laid out to give us the information to collect the most valuable set of samples ever, samples of Mars, that we'll later bring back to Earth. Samples that are addressing the very simple question about, is there life elsewhere, a child might ask, related to Mars. This Mars mission is a true astrobiology mission, focused on the origins of life away from Earth and the conditions in which life might emerge. It has been hard to get this mission ready, and the team is hard at work right now. Who knew that we would see a virus as the highest risk to a timely launch of this mission, which last month was so aptly named Perseverance? NASA and its partners are doing everything possible to launch this mission on time because, just like the mission that will follow it, it is Perseverance that will ultimately achieve the big goals that yet again change the history books. In 2026, we want to launch the first mission back to Mars that is actually a launch vehicle that will lift these samples out of Mars and gets picked up by a European mission, and together as an international partnership will bring the samples back to Earth for study. The most precious samples at that moment in time will have extraterrestrial samples to study questions of life and many beyond that. But right now, as we prepare the Mars 2020 mission to launch, we find that the core qualities of Perseverance, so essential to this mission, are proving critical in these final weeks on Earth. And we will rely on this quality going forward, knowing that we will have to successfully land and operate the Perseverance rover on the Martian surface. All missions face own obstacles, but we'll keep going to chart a new story of humanity on another planet and in space in ways we cannot even comprehend yet. That is the story of exploration, and the seed of perseverance in which we all rely on. A seed that grew from a necessary question of hope, a question of curiosity, and it's a quality that ultimately will bring it to its successful conclusion, perseverance. We are hopeful because the next generation who will complete this journey is inspiring. I've been using the words earlier in this talk from one of the students to frame this. In fact, it's Alex Mather, the 13-year-old who named the Perseverance rover. And I will end this talk with his words. Words about how humanity will persevere through exploration and beyond in the future.
Curiosity, insight, spirit, opportunity. If you think about it, all of these names of past Mars rovers are qualities we possess as humans. We are always curious and seek opportunity. We have the spirit and insight to explore the Moon, Mars, and beyond. But if rovers are to be the qualities of us as a race, we miss the most important thing: perseverance. We as humans evolved as creatures who could learn to adapt to any situation, no matter how harsh. We are a species of explorers, and we will meet many setbacks on the way to Mars. However, we can persevere. We, not as a nation, but as humans, will not give up. The human race will always persevere into the future. My name is Alexander Mather, and that's why I chose Perseverance as the name of NASA's next Mars rover.
Don't you love this quote by Alex Mather? I certainly do. I love it very, very much. And as I'm sitting here, I'm thinking of all of you, and I'm wondering about your goals, your drive for exploration, or whatever drives you, and your stories of perseverance in it. Share those stories. Share them with us. Share them with others, because those stories are inspiring and are exactly part of what drives us going forward through exploration, to places we've never gone before, to experience things we've never experienced before. Thank you so much.